In this video now we will see how we will be generating these embeddings, the conversion, if you like, from the tokens into vectors. So let me just draw this, the final kind of goal. So this kind of an embedding encoder that will take as input the token, and will create a vector of some length that is going to represent that kind of token. So we've seen from an earlier video on tokenization that at the end of the day, we are getting a sequence of tokens for each that corresponds to our text. So let's say 1535, things like that. That are coming at the input of this embedding encoder, and our vectors will be d-dimensional, so we will be using the letter D to represent the vector. So vectors will be represented with the usual letter X that we represent also data. So X is going to be, so this is X that corresponds to 1535 token, and so on and so on, and X is going to be d-dimensional. Okay, so that is the role of the embedding kind of a layer. As we have seen, every neural architecture requires a vector at the input in order for it to be able to produce a prediction that corresponds to the task that we have at hand. So and an obvious way to actually create a vector that, as it turns out, may not actually work very well is to encode these vectors in the so-called one-hot encoding. So let's assume that we have a word that corresponds also to a token that is called hotel. Okay, so this is our token over here, and this indeed corresponds to the a token of 1535. That's the token ID. So one way to encode the hotel into a vector is to we have a vocabulary size, which is the total number of tokens that the tokenizer kind of produced for our corpus, and so we have all zeros, and at the 1535 location index of this kind of vector, we have a 1. So this is d-dimensional, where d is the vocabulary size. So in this case, we have the cardinality of our vocabulary. Now we'll be symbolizing the vocabulary, a set of all the tokens, in other words, that the tokenizer produced, with capital V. And this sometimes in the literature you use that to represent the so-called cardinality operator. In other words, how many elements do we have here? Sometimes we'll use this cardinality operator, sometimes we'll skip it for kind of keeping the notation a bit simple. So that's basically my so the representation of the hotel, and it's not really difficult to see that if we are to use this representation, we are going to have some issues with every processing that involves some form of extraction of correlations or patterns in a text of corpus, and one way to actually show it is, which always involves some form of a dot product. We've seen in earlier videos that most neural architectures will involve projections, and so projection represented by dot product is going to create the following kind of issue. So let's assume that I have another word that it is the X is let's say 2010, and this word corresponds to the word motel. Okay, so following, if you like, the same kind of approach, we will be positioning a 1 at location 2010, and so on. So we see that by construction, the two vectors are orthogonal, and which means that their dot product, if we write the dot product over here, will actually be 0, and which means that it causes the following kind of issue. The two words are very similar. So what we expect to see from their dot product or kind of operation, that their dot product of similar, semantically similar words to be the maximum possible. So that kind of requirement is not satisfied from the kind of a one-hot encoding representation, which is obviously a kind of a trivial representation. So our task here is to come up with representations, embeddings, that are semantically similar words are in some d-dimensional space very close to each other. So let us try to see an example now of how this will look like, kind of a demo. And if you go to the site, then we actually can see here, let me sort of bring it up a little bit. So we actually can see here the representation we are actually after. The representation that we're going to be dealing is called word-to-vec. That construction from tokens, IDs into vectors is called word-to-vec, and it is in the category of representations actually called context-free representations. And we'll clarify now what is context-free and what is contextual kind of representations in a moment. But let's see exactly what we see here. We see here a cloud of points, and each of these points represents a word. And the construction is such that, let's say that we search here for the word car. By the way, the vocabulary size is 10,000. And the number of dimensions, the D that we have actually specified earlier, is 200. So these words live in a 200-dimensional space, and obviously we have here a 3-dimensional space. So what we have done is we did dimensionality reduction. This dimensionality reduction is achieved with a technique called principal component analysis. And PCA is very similar to the singular value decomposition operation that you may be familiar from linear algebra. And so we went down from 200 dimensions to three dimensions. So one obvious thing that we cannot really do here, we cannot really extrapolate the geometric similarity, the geometric distance in the 3-dimensional space back to 200-dimensional space. That we cannot do that. So, but what we can do is we can look at the geometrical distance at the original 200-dimensional space by, let's say, searching for a word, let's say car over here, and we can actually see how the representation that word2vec has generated associates very similar meanings to the other words in our vocabulary. So for example here, driver, cars, automobile, race, racing, vehicle, and so on are at the top positions. And at the bottom, this could be a horse, businessman, and so on. Let's see how this will be achieved, how we can construct this representation. And we need some kind of a guiding principle in this kind of construction. And this came from a linguist, Firth, who's actually said the following many decades ago. A word's meaning is given by words that frequently appear close by. Okay, so all of the keywords here are the following: frequently and close by. And the moment you hear the keyword frequency, then in your mind should actually come the sort of frequentist view of probability. So first pointed to a kind of a probabilistic way that we are going to do this kind of construction. That's point number one. And also pointed into some form of windowing that we need to implement in order for us to extract the meaning of a certain word. All right, so we will be calling this window the context, and despite the fact that we are mentioning here the word context, at the end of this discussion we will all realize that this is a context-free representation. So let's wait until that point. And here's what is going to what we are going to do. We are going to be given a corpus of a corpora of documents. So, for example, let's see. Over here we have a corpus of documents that have to do with, let's say, financial news. And here we have the word banking being quoted. And for this specific representation of the word kind of banking, what we'll be looking over a context of size, let's say 2 words before it and 2 words, let's say, after it. And we will be counting effectively, therefore estimating probabilities. Therefore, estimation of the probabilities are going to be associated with some kind of prediction of the words, of the occurrence of the words that are appearing next to it. So let's see a bit more specifically. Let's write this kind of down and see how these probabilities will look like. And evidently will take the form of posterior probabilities. So let's draw. So we have the concept of, let's say, the center word, that it was the word banking. So the center word is actually coming in. We'll be representing the words with, let's say, the letter W. I mean, it is definitely a deviation from what we have seen earlier, but we will be representing these words with W in terms of notation. Okay, so this is WT. We'll be using now the index also to indicate that this is basically the center word, and as compared to earlier words, we'll have T minus indices, and as compared to future words, we have T plus indices. So we have WT coming in, and this is going to be a vector that it is associated with the one-hot encoding vector that we have seen earlier. So we will be doing the one-hot encoding at the input of our encoder. Okay, so vector in, vector output, in other words. And we are going to, over here, predicting let me draw it like this. For, let's say, probabilities, the y hat of t minus 2, the y hat of t minus 1, the y hat of t plus 1, and the y hat of t plus 2. In other words, if we are to go back into the site, what we will be doing the following. So we will be predicting, we'll look at the center word, let's say into, and we will be build a machine that will predict with high probability of being correct. In other words, the words that are appearing next to it. Okay, so into, we have a context window of 2, as we discussed, let's say in this case. So the words that are appearing next to it in this case is problems and turning, banking and crisis. For banking, it is turning and crisis. So we have a whole bunch of these kind of sentences, and each sentence kind of is going to give us an opportunity to, each word, in fact, is going to give us an opportunity to create, if you like, a data set. We'll see that in a moment, how we will do that without really much of an issue. And our kind of will build a neural network that it will give us at the output y hats. These y hats have always been for us posterior probabilities, so they will be predicting the word that is appearing immediately before the word of interest, the center word as we call it, given the presence of the center word. Okay, so that is really the sort of aim of our construction. And to do so, we need this kind of a training data. And this is a table that kind of explains how the training data can be obtained very easily from our text. And so we don't have any problem generating this data from existing text, as much data as we want. So let's assume that we have an input sentence, let's say in our corpus, let's say Claude Monet painted the Grand Canal of Venice in 1908. And as we can actually see here, it's very easy to generate a data set that will have as ground truths the words that are preceding. Let's say Claude is not preceded by anything, but it is followed by Monet and painted, and so on and so on. So painted is followed by Claude Monet and is preceded by Claude Monet and followed by the Grand. And so we can actually build quite a lot of data that can construct a lot of training data for our purpose over here. So training data is not going to be a problem, and that's what we will do. And at the same time, we will need to go back in an earlier video where we have seen the concept of maximum likelihood, and kind of construct that machine that is going to take the center word and predict the posterior probabilities of the corresponding contextual words. And so we have here a context that will be, let's call this context capital C. So capital C is in this case let's say the context. It's of let's say size 4, let's call it plus or minus 2. And that's basically what we will be doing. We will now see the elements of that machine, but how this machine get constructed, I think it should be motivated from maximum likelihood, as we always have done in the past. So let's write down so we always had in two probability distributions. If you revisit that video on maximum likelihood, one was called P data hat, and the other it was actually called the P model. So the table that we have just saw had over here will actually give us the P data hat because it has the sort of training data. And so let's write down the nature of this P data hat as a posterior probability. So in this P data hat we have the, let's say, WT minus C. In fact, C in this case will be just 2, because we will insert this minus over here, T minus C, WT minus C plus 1, dot dot dot, WT plus C. These are all the words that are in the context of the center word WT given WT. So no surprises there that this P data hat is a posterior distribution. So let me call this center word, and this will be the context words. Context words. And similar to what I have seen earlier, we need to have now a P model. We need to construct a hypothesis. Our P model is going to be of some similar nature to our P data hat, because as we discussed, we had to produce a P model that is going to be parameterized by a parameter set theta to be able to approximate that P data hat as closely as possible. So our P model, no surprises, that will be of a similar nature. Let me put some dots here to make the notation a bit simpler. Okay, so this will be given WT comma theta, where theta is the set of parameters, obviously the set of trainable parameters as we as we have used this letter before. And now we're going to make an assumption that is actually called, so let me write it down a bit more specifically here. This is called naive Bayes assumption. In order for us to be able to simplify the architecture of this kind of neural network, this assumption helps quite a bit. And what this assumption is actually saying is something pretty straightforward. So let me write down the naive kind of Bayes assumption over here. So the naive Bayes assumption is suggesting that given, and it's not being used only in this kind of application, naive Bayes is a sort of a well-known sort of prediction kind of assumption that can be used for many other kind of data sets. But here it means that given the center word, all context words are independent of each other. So this is the assumption behind naive Bayes, and it makes some sense. It's a simplifying assumption, and how successful this will be, of course, it will be judged at the end from the results. So over here, given this assumption and remembering the so-called conditional independence that we have reviewed much earlier in another video, we can actually write this conditional probability as a product of other conditional probabilities. So we can actually factorize this, in other words. Times P model minus C plus 1 given WT comma theta times, and so on. Finally, we have this last one. Let me put some dots here to make the notation a bit more clear. Times P model of WT plus C given WT given theta. So this is going to be written as the product from j is equal to minus c to j is equal plus c, where j less than 0 of P model of WT plus j given WT comma theta in a bit more compact form. So this is the naive kind of Bayes assumption that governs the P model, and this actually also gives us some ability to kind of decouple the architecture. We'll see how this decoupling takes place. And the next step is to define, if you like, a loss function. And this loss function should not be any different from the maximum likelihood loss function. So I can write here that according to ML, to maximum likelihood principle. Of course, we recognize that the naive Bayes assumption, given that the fact that we have probabilities over here, then we need to be operating in the log domain, and we'll do that. But according to the maximum likelihood assumption, the principle, so not assumption, principle, we need to minimize the following kind of loss. And for those who have forgotten about this kind of loss, I suggest that you look at the maximum likelihood treatment that we have seen. This loss, it is an expectation, negative of the expectation, which of course replaced by a sample mean as an approximation, is a minus the expectation of what was then back then. We had x's and y's. So over here, the x's that are actually coming in is the center word, and this is the X, and what is the Y? The Y is the context word. Okay, so we have here the X. So we have examples that consist of X, which is WT, and Y's, which are the WT plus J. So all of the set of words, in fact. So an example consists of the center word and the set of the context words that are, of course, distributed according to P data hat. Of the log, this is the log domain, if you like, of the log of the product, sort of from J is equal to minus of our P model, from J to minus C, for J is equal to plus C, the P model. W T plus J given WT, comma theta. So this is our maximum likelihood principle from the first principles kind of perspective, and how it is written in the specific problem here. All right. So this is our sort of equation, the equation of the loss function. So we need to construct an architecture that it will model this, and will minimize this kind of loss function in order for the architecture to be able to predict accurately the context words. And the architecture actually looks like this. So we have the typical projection that we have seen in dense layers. So we have as input the context word, the center word WT. Definitely, as we discussed, the WT has a span of cardinality V dimensions, so it's pretty sizable. So typical size of vocabulary sizes are, let's say, 10,000. We've seen it kind of earlier in the demo. This is typical sizes for, let's say, your Alexa smartphones. The number of words that they're able to understand are typically in the few thousands. And of course, when you do Google search and so on, you are looking at much larger vocabulary sizes. So typically up to 1 million kind of tokens are actually present there. So the center word, let's say, is going to be, let's say, the car from the demo. And this will actually need to be reduced down to D dimensions, as we discussed. So the center word will live in a lower dimensional space. And we expect, we intuitively understand why it has to be lower dimensional. And the reason is that the semantic, the meaning of word, let's say hotel and motel, are going to be, let's say, or in this case, kind of car and driver, are going to be associated with a kind of a lower dimensional space of D dimensions. Okay, so we have here our D-dimensional vector. We will be calling this Z. And this projection, as we have done earlier, will be done with a dense matrix. This dense matrix W, capital W. I hope there are not too many W's. It's a small w, this is a capital W that has a size of cardinality V times D dimensions. So Z will belong to R to the power of D. And then what we need to do now is we will be taking this Z-dimensional kind of vector, and we are inverting this kind of projection, so to speak, with the help of a W prime matrix to produce a vector. Let's call it this vector Z prime, that it will be such that when I normalize it via the softmax operator to produce the posterior probability at the output, which is, let's say, y hat, that it will be give me, let's say, a diagram, a plot that will look like this. So if this is, let's say, is the word car, the one hot encoded version of the word car, then there will be a posterior probability distribution that this index will correspond to the word, let's say, driver, and some other indices we've seen from the demo will be there. And this, of course, will be v-dimensional. So we went from v-dimensions to v-dimensions because our context words are in the v-dimensional kind of space. And we are actually, by doing so, we are compressing down the dimensions to d and creating, if you like, the right representation. If the representation is the right one, then we are going to be able to predict the context word with very high probability, correctly with a very high probability. And of course, we have not only just one context word, but we have minus c to plus c, like 4. So we are going to be indexing this matrix with j that we have met earlier, that indices the context word. So these are all j's. So if we understand the approach for one of the context word, then we can understand for many. In fact, for other context words, we will still start. So we will have to jointly optimize, if I may draw it like this. I'm not so sure if this is going to be the right drawing, but if you can draw it like this, you can see that there's going to be another matrix. Let's say W j plus 1. That will give me zj plus 1 vector, and via a softmax operator, I'll be producing a y hat j plus 1 that it is associated with a posterior probability distribution. In this case will be, let's say, engine. This one will correspond to engine, because engine is was a very frequent contextual word that it was quoted next to the word car in my corpus. So I hope it's actually clear what is actually happening over here. So as we've seen earlier, we in other kind of videos, we can actually write down the forward propagation equations to just convert the diagram into a set of equations. So these are very straightforward. So we produce the z, which is the wt transpose w. So this will be t times 1. Then we have zj prime as the z times w prime j, and the y hat j is a softmax of zj prime. Definitely we have a loss that, as we discussed in the maximum likelihood section, we have a prediction over here. This prediction is a classification prediction because we are trying to produce the posterior probability distribution. Let me write this down again. Y hat j is the probability of w t plus j given wt comma theta. Okay, so this is the a posterior probability distribution we need to form, and we can go select as the context word the word with the maximum posterior probability for that specific index kind of j, and that's how we will form the loss. So the cross entropy is between the predicted sort of a word and the ground truth word, and we've seen in this kind of Claude Monet example how the ground truth word was produced. Okay, so this is going to be the the loss, and of course we have a set of trainable parameters that correspond to W and Wj. These are the Wj prime. These are the matrices. Of course we have other matrices as well, so I may include them as well as shown over here. Okay, so that's basically it. And since we are going to form that kind of a network over here, we are going to train it, and we are going to, at the end of the day, at the end of this kind of training kind of process, what we're going to see is we're going to get the matrices out of the matrices that the theta stars at the end of the training process. So let me write down at the end. We get the theta star. From the theta star, of course, we get the W star. And it's really this W star that we are going to store. We are not really concerned about anything over here other than the W matrix. And the reason why we don't concern of anything like that is that we are trying to create a lookup table. The lookup table is going to have as indices the token IDs that, of course, are v-dimensional. And we are going to mean this W matrix is going to correspond to the following dimensions. So W will have D columns and will have V rows. As you understand, these are the dimensions of W to make the Z D-dimensional. And therefore, the row, so the moment we have a token ID, we can actually look up this W matrix as a lookup table to retrieve so this is basically the token ID. So the sort of whatever row card, let's say, corresponds to 1535, a row of this matrix W star is going to correspond to the d-dimensional vector. So we are actually able to get the representation according to this word-to-vec construction from this matrix. And these matrices are the ones that are typically stored in hubs, and you're able to retrieve those representations for any construction, not only word-to-vec, but other embeddings constructions by effectively a single line of code in the popular APIs, PyTorch, enhanced with transformers, or TensorFlow Keras enhanced again with transformers. Okay, transformers is really a very, I will call it, popular library to work in natural language processing. So we'll be seeing some examples of that a bit later. Okay, in the next, now that we have our embeddings, what comes next is we are going to start using some of these embeddings in our tasks, the tasks that we're interested in, starting with the task of language modeling. But I wanted to emphasize one kind of key observation here before we close this discussion. And the key observation here is that this word-to-vec representation is a context-free embedding construction. And you can actually wonder why on earth this context free, since we are actually then in the network we have the context all over us. And the reason why it is actually called context free is not that we are not using the contextual words to be able to follow the first kind of principle and predict, if you like, with a good probability the words which are surrounding the word of interest. But it's because at the end of the day, if I had, let's say, a corpus of documents, let's say on news, and in the news we had, let's say, the quote of the word bank from some kind of financial kind of news clips, and the word bank was quoted from some kind of disaster or some kind of flooding that happened, then at the end of the day, the word bank will have one vector as a representation and not two or three or whatever. So this is the reason why I actually call this construction a context-free embedding, and we will see that more advanced constructions are possible. Those are somehow merged together with the tasks that we have to do. And we'll see them when we deal with other kind of architectures in another video.